Take a deep breath. We finished our beautiful graph of the trace determinant plane. And now we're going to say, how does this apply to the harmonic oscillator? Are you sick of talking about the harmonic oscillator? Too bad, because next up is a chapter where we talk about harmonic oscillators, specifically forced harmonic oscillators. So before I do that, I want to make a few more comments on the trace determinant plane that didn't fit in the last video. It was already quite long, you may have noticed. So specifically, I want to say that the trace determinant plane is an example of a specific kind of plane. It's an example of something that's called a parameter plane. And what that means is just a plane of parameters, right? We have the XY plane, those are variables. But the trace determinant plane are parameters, because if you think about our matrix, right, if A is the matrix A, B, C, D, the entries of this matrix are parameters. Okay. And so the trace depends on parameters and the determinant depends on parameters. So yeah, we're plotting qualitative behavior based on parameters. That's why it's known as the parameter plane. And again, what are we actually graphing? We really are graphing qualitative behaviors of solutions. This is something that we don't graph like this very often, right? This is almost like more of a chart or a picture, but it is on a plane. And works in relationship to the axes and in relationship to this curve, this quadratic function, which is like really, really quite wild and very cool. So it's a really kind of altogether different kind of graph based on the relationship of the trace and the determinant of a matrix, which again are defined by these parameters. So that is pretty cool. And another big thing is that the trace determinant plane does not tell us everything. So it tells us a lot of things, but it's missing some information. Specifically, when we look at the repeated real parabola, there's no way to get information about whether we have one linearly independent eigenvector or two linearly independent eigenvectors. We can't get that information from the trace and the determinant. So number of linearly independent eigenvectors on the repeated real parabola. There's no way to get that from the trace and the determinant. And furthermore, the direction of the spiral sources and sinks. You just can't get that from the trace and determinant. There are matrices that have the same trace and same determinant that have different directions of their spirals. So these are some things that it can't cover, but it still does a really good job of giving us some qualitative information. Now, with that out of the way, how does this apply to the harmonic oscillator? Well, let's revisit for the 500th time. M times the second derivative plus b times the first derivative plus k times y equals 0. And again, m is the mass. It needs to be positive. B is the damping. It has to be non-negative. K is the spring coefficient, which must also be positive. And we've turned this into a system many times. I could have you do it again, but I'm just going to save some time and give you what the system looks like. It's 0, 1, negative k over m, negative b over m is what this looks like as a system with the position and the velocity. So what's the trace of this? Trace is the sum of the diagonals, which is just negative b over m. And the determinant is 0 minus a negative, it's just k over m. So the harmonic oscillator actually has a really convenient trace and determinant. And because m, b, and k are either positive or non-negative at the very least, the trace must be negative. The determinant must be positive. This could technically be 0. But this has to be strictly positive. So the trace determinant plane, we really only have to look at the second quadrant. Oh gosh. we really only have to look at the second quadrant for the harmonic oscillator, and we can do a little picture for this. So let's do that. Let's steal the second quadrant. Da, 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 da. Here's the second quadrant. And if we steal the second quadrant, here, let's bring it over here. We have all the information that we need. And again, we actually don't have this degenerate case because that's when the determinant is 0, but we know the determinant is strictly positive. But we have these other 4 cases because the trace can be 0. So again, this is the trace axis, this is the determinant axis, and we're just looking at these 4 cases, which we've already talked about, right? This is when it's undamped. It's undamped when the trace is 0. Because that's when the damping coefficient is 0, right? M will never be 0, and it certainly can't be infinity. So that's undamped. What was this? This was the underdamped. Both of these have complex eigenvalues. Underdamped was that specific relationship between B and M and K. And then we said, okay, this was that borderline case. This was the critically damped, where it's like kind of undamped. It's almost spiraling, but not quite. It really functioned quite similarly to the overdamped, which is here. So by looking at the trace and the determinant, we can quickly tell which of those 4 situations that we're in that we talked about in the last section. Undamped, underdamped, critically damped, or overdamped. And remember that, again, how I talked about it is the level of damping affects which of these we are. If B is 0, we have no damping. If B is relatively small, we were underdamped. If B is quite large, we were overdamped. And if B is, between small and large, we're critically damped. And I phrased it by saying it's really just the relative size of B. And that's true. The further left we go, the more damped we are, relatively speaking. The further left we go is just what happens as B gets bigger. The damping coefficient gets bigger. And of course, it's the relationship between the damping and the spring coefficient and the mass. It's that relationship that matters, so it's not just that. But certainly, yeah, the more left we go, if everything else is constant, the more left we go, the more damped we're going to be. And you can see that in another way with this picture. That's kind of cool. And again, I kind of cut this out, but it doesn't matter what your entries are, what your A, B, C, M, B, Ks are. Lambda is still the trace, plus or minus the square root of trace squared minus 4D, all over 2. This is still the case. We're just looking at a more specific matrix, where A is always 0, B is always 1, C will be this relationship, and D will be this relationship. Well, I said B is always 1. Not this B, not the damping coefficient B. And that's how the trace-determinant plane kind of works with harmonic oscillators, which is kind of fun. And that's all I have to say right here. That's pretty much it. Enjoy. Bye-bye.